Hi everyone, welcome back to my channel. Today I'll be diving into one of the most fundamental concept of computer science, hashing. Now I'll walk through what is hashing, what are the different types of hashing, how it works in real world scenarios. Let's get started. Firstly, I'm Kaushik, currently a second year student at SCCE.
First up, what exactly is hashing? In simple terms, hashing is a process where you take data of any size, this could be a file, a string, or even a password, and convert it into a fixed size value. You do this hashing function, think of it like converting a name into a unique code. For example, if I take a word apple, the hash function would turn into a unique code like 1234 or ABCD. The cool part is that even if you change one small part of the input, the output changes completely. Hashing is a core tool in areas like cryptography for securing and storing passwords and in databases or hash tables for quick data lookups. What's really powerful about hashing is that no matter how large is or small is the output or the input also, the hash function always generates a fixed size value, making data retrieval super fast. So, why is hashing so important? One of the biggest reasons is performance. Hashing provides time complexity for both lookups and insertions. That means, on average, no matter how much data you have, it only takes a constant amount of time to find something or add new data. This is crucial in applications where speed matters, like in search engines, where billions of queries need to be processed in real time. Another big reason is data security. Hashing is used to verify the integrity of data and secure things like passwords. For instance, when you log into a website, your password isn't stored as plain text. Instead, it's hashed. This means even if hackers gain access to the database, they only get the hashed values, which are almost impossible to reverse. But hashing isn't perfect. One of the main challenges is collisions. That's when two different inputs generate the same hash, while it's rare with good hash functions. It can happen, and handling those collisions effectively is. Now let's talk about static hashing. In static hashing, the size of the hash table is fixed for the moment it's created. This means that once you set up the table, it doesn't change, whether you add more data or not. When you input a key, the hash function maps it directly into the bucket in the table, and that's where the data gets stored. While static caching, it's fast and simple to implement. It's best used in situations where your data doesn't change much. For example, in small cache or compiler symbols where the data size is known and won't grow. The downside is the static hashing can't handle unexpected data growth. If the more data comes in than you anticipated, you might run into collisions and the performance could degrade. Also, if you overestimate the data size, you will have a lot of empty buckets leading to wasted memory. That brings us to dynamic hashing. This is more flexible technique. Unlike static hashing, where the table size is fixed, dynamic hashing allows the table to grow or shrink the data changes over the time. When a bucket gets too full, dynamic hashing can rehash the data and distribute it across the new large buckets. This type of hashing is especially useful in systems like databases where the amount of data is unpredictable. For example, when you are managing a user database, you don't know in advance how many users there will be. Dynamic hashing can adjust automatically to handle more data. There are two main techniques used in dynamic hashing: extendable hashing and linear hashing. Extendable hashing. This uses a directory of pointers to buckets, and when the bucket overflows, the directory size doubles and to add new buckets. This avoids the need to rehash all the keys. And linear hashing. This technique adds new buckets one by one, reducing the need of large scale rehashing all at once. The incremental approach is a great way to handle growing data without slowing down the performance too much. So what happens when two keys generate same hash? This is called collision, and it's a common problem in hashing. Thankfully there are some effective ways to handle this. The first method is called chaining. In this method, each bucket holds a linked list of keys that map to the same bucket. While this works well for small collisions, if too many keys collide, the linked list gets longer and slowing down the lookup times. And the second method is opening addressing, where instead of storing all the colliding keys in one bucket, we find the next available slot. There are few techniques for this: linear probing, quadratic probing, and double hashing. Linear probing: search for the next empty slot sequentially. And the next one is that quadratic probing. Look for empty slots by increasing the interval at which we search. And double hashing. This uses the second hash function to calculate where placed to the next data, minimizing the collisions even further. Let's now compare static and dynamic hashing. If your data is fixed and predictable, static hashing is faster because it does not require resizing. But if you are dealing with data sets that can grow or shrink, like in large scale applications or databases, dynamic hashing is the way to go. Dynamic hashing might have a slight performance overhead because of the resizing, but it ensures you never run out of space and it reduces the chances of collisions. Static hashings, on the other hand, can lead to wasted memory or slowing performance if the data size exceeds expectations. Looking into the future, hashing is evolving in exciting ways. For instance, adaptive hashing is becoming more common, where the hash function adjusts itself based on the data distribution. Then there is distributed hash tables, which are used in peer-to-peer networks like BitTorrent. This allows data to be distributed across multiple nodes, ensuring fast access without any single point of failure. In cryptography, there is growing research into quantum hashing aimed at developing algorithms resistant to attacks from quantum computers. And in machine learning, hashing is being used to speed up future lookups in huge datasets, making AI model more efficient. In conclusion, hashing is a fundamental concept that powers a lot of technology we use every day. Whether you choose a static or dynamic hashing depends on the specific needs. Static hashing is great for predictable, unchanging datasets, while dynamic hashing is ideal for data that grows and changes over time. And with innovations like adaptive and quantum hashing on the horizon, there is a lot to look forward to this in this field.